Hey everyone, this is just a short presentation that I made about the problem I'm working on. Just wanted to share with y'all. So imagine I want y'all to look at something in front of you, reach out and touch it. I'm touching the corner of my laptop. Now what does that mean when you're able to touch it? There is some distance from your eye to what you just touched, and that distance is known to you. It's known to you because you figured it out and were able to touch it. Close one eye, it's a little bit harder. Close your other eye, it's a little bit harder, but you can still do it. Now, the fact that you can do it means that you can look at something, figure out some distance, and then command your finger to go out and touch that distance. Now, zooming out a little bit more, what does that mean? I'd argue that it means that we represent distance not in meters, feet, centimeters, inches, or whatever, but by our actions. Our actions. What we can do. Now, why is this important? Let's compare this to how robots would do it. Let's say we have some simple problem, like going through a door. Some poor intern would measure the width of the door. Another intern would measure the width of the robot. And using some LiDAR, the robot would estimate the distance of the door. If the robot thinks it's not as thick as the door, it goes through. Now this is a little unnatural because all has to be done in meters. And like we just established previously, we don't do that. And the reason why this is a little problematic is because there are now billion-dollar industries to making sure that cameras keep their calibration. I mean, this is ridiculous. That's a strong word, but why does the camera need to be this rugged? It just doesn't check out. So my goal is to bring this to robotics. It doesn't have to be that ruggedly calibrated. So first, I tried to tackle the throwing problem. Can we throw with embodied distances? Now before you throw, you need to learn how your arm works. So this is how I learned how the arm works. Us knowing how our arm works is basically establishing a mathematical model for the robot. What a human is to knowing what the arm is, it is to the robot establishing a mathematical model. I know that's a lot of M's. But I wave the robot's arm around and take data from waving it around. I can create an input-output mapping. And the more I wave it around, the better that model becomes. I can predict how much effort it does, how quickly it does it, just by what I tell it to do. Then, I set up an optimization problem. I use basic physics and inverse kinematics to do an initial guess. And then the robot just practices throwing. And it practices really quick, because it's a computer. And eventually, it's really accurate. Now, the reason why I didn't stick with throwing is because at the end of the day, this is about as far as it can throw, which just really isn't that far. What happens is, if it goes too fast, it just doesn't do what we tell it to do. And it makes this really bad noise, and it stops working. This is it going too fast. Now, golfing has a similar loop, a similar step, similar procedure, but instead we have cameras to track where the ball is and where the club is. Then we track the motion of the club and the motion of the club in the camera, and boom, we know how to golf. Here's a video of the robot golfing right now. It's still a work in progress, and I hope to get more videos to you guys soon. Thank you all for watching. And let's make this thing Tiger Woods. Come along for the journey.